This is week 26, homework sheet page 1, number 6. Name the following halocarbon. Now, when we have a halocarbon, we know that the suffix we add is going to be an O, like in halo. And we're going to add that O suffix to whichever halogen atoms are present in the halocarbon. If we look at this particular one, we see that we have two bromines, one here and one here in this halocarbon. Therefore, bromine is going to have the suffix O added to it. So we're going to have the partial word bromo in this name of this halocarbon. Now, before we can use the phrase or the term bromo, we have to figure out what type of a hydrocarbon is the parent carbon chain in this particular molecule. And we do that by counting the number of carbons in the chain. 1, 2, 3, 4, 5. So there are 5 carbons in this particular chain. And if there are 5 carbons, then we use the prefix pent, which is for 5. You should know all the prefixes: meth, eth, prop, bute, pent, hex, hept, oct, non, and dec for 1 through 10. So this parent chain is a pentane chain. Now this particular pentane chain has 2 bromine. So if there are 2 bromine, we call it di-bromo. The di means 2. Bromo is bromine with the O suffix added to show that it's a halogen. Now the only thing we have left to do is to tell where those 2 bromines are situated on this carbon chain. And we see that they're situated on the first carbon. Now, this could be the first carbon, this also could be the first carbon, but we're always going to count the carbons from the closest side to wherever the functional group is attached. And since the bromines are attached here at this carbon, we'll call this number 1. So both bromines are at carbon number 1. Therefore, we're going to call this molecule 1,1-dibromopentane, showing that both bromines are at the position 1 at the end of the chain. There are 2 of them. It's bromine, and the O suffix tells us it's a halogen. Pentane tells us that there are 5 carbons in the chain and that all of the bonds are single bonds, hence the ending -ane. Now I've switched the positioning of the bromines. So there's a bromine at the end, and there's one in the middle of the hydrocarbon chain. If that's the case, then we would call this 1,3-dibromopentane because there's a bromine at position 1, and 1, 2, 3, there's a bromine at carbon number 3. Now I've repositioned the bromines where they were, and I added chlorine here at position 3 just to show you how you would name this. So here we have 1,1-dibromopentane, but it also has chlorine. So I start at the end and I have 1,1-dibromo, and then I have at carbon number 3 chlorine, so we add the O to show it's a halogen, 3-chloropentane because it's still a 5-carbon hydrocarbon with all single bonds. So 1,1-dibromo, 3-chloropentane. This is week 26, page 1, number 9. Draw a structural formula, then name the halocarbon with the following condensed structural formula. Now, the first thing we're going to do when we look at one of these condensed structural formulas is find all of the carbons. I circled the carbons in red. Now, we know that each carbon can have only 4 bonds. I've shown the 4 carbon bonds like this. Each carbon can have only 4 bonds because carbon has 4 valence electrons, and in order to have a full set of valence electrons it needs 8, so it will share each of its valence electrons with an electron from whatever it's bonding to. So each of these carbons can have 4 bonds, so let's talk about what things each of these carbons are going to bond to. This particular carbon is going to bond to 2 hydrogen, that makes 2 bonds. It's also going to bond to fluorine, that makes 3 bonds, and it's going to bond to the carbon that's next to it, that makes 4 bonds. This carbon here is going to bond to this particular carbon. It's going to also bond to this hydrogen and this bromine. That's 1, 2, 3, and then it's going to bond to the carbon on the other side of it for 4 bonds. Now this little configuration here is a bit confusing, but it's basically telling you that there are 4 sets of CH2. It could be written out in this way, CH2, 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 but since it's a condensed structural formula, we put CH2 with a subscript of 4 outside of the parentheses to show that there are 4 of this particular part. Each of these carbons in here are going to bond to 2 hydrogens plus 1 carbon on either side. So that makes 4 bonds. 1, 2, 3, 4. And now the last carbon in the chain will bond to the carbon before it, and then 3 hydrogens around the outside, and that gives it its 4 bonds. So we can draw that out in a larger scale model. I've drawn a chain of 7 carbons because we have 1, 2, plus 4 is 6, and 1 more is 7. So there's 7 carbons in this chain. I've also shown that each carbon has 4 bonds, so each one has 4 little lines around it showing the bonds. Now I'm going to draw all of the hydrogens in black. This first carbon has 2 hydrogens. It also has a fluorine that it's bonded to. I'm going to draw the fluorine in green because we need to know where the halogen atoms are in this chain. Now this second carbon is bonded to the carbon before it. Here, as you can see, it's also bonded to a hydrogen. It's also bonded to a bromine, which is another halogen. Now, we can't tell from this formula whether the hydrogen's going to be up here or down here. So I'm not going to fault you for where you put it. It doesn't really matter at this point in your chemistry career. The third, fourth, fifth, and sixth carbons are all the same. They all have 2 hydrogens and a carbon on either side. And now the last carbon has 3 hydrogens around it, plus the bond to the carbon before it. So there we have the structural formula of this particular halocarbon. Now we need to name it. So we're going to start by naming the parent chain, which has 7 carbons, as we already determined. And a hydrocarbon with 7 carbons and all single bonds is going to be called heptane. Now there are 2 halogens. One is fluorine and one is bromine. So we're going to say 1. Fluorine is at the first carbon. Now I know we started counting from the other side last time, but we always start counting at the side that's closest to whatever functional group we're identifying. So since the fluorine is at this end, we'll say this is carbon number 1. So 1 Fluoro, we added the O ending to show it's a halogen. The second carbon has bromine, so 2-bromo, and heptane is the whole parent chain. And that's the name of this particular molecule. Week 26, page 2, number 11. Draw a structural formula for 1-octanol. What type of alcohol is it? Well, we know that the OL ending is indicative of the structure of an alcohol, and oct has to do with 8 carbons in the chain. We know that if it says 1-octanol, we know that the hydroxide functional group, which is typical of an alcohol, is at the first carbon. So let's draw that chain. I showed that each carbon has 4 bonds available by making 4 little lines around each one. Now, an alcohol has a hydroxyl group, and this one has it at the first carbon, so I could put it either at this carbon on this end or this carbon on this end. I drew the hydroxyl group in green just to show that it's the functional group. Doesn't have to be any special color. The rest of the bonds are going to be filled up with hydrogen. So this is the structural formula of 1-octanol. Now it asks us, what type of alcohol is it? The carbon containing or bonded to the hydroxyl group has only one other carbon attached to it, and so this would be a primary alcohol. Now I have changed the position of the hydroxyl, and this causes us to have to name this particular alcohol a little bit differently. It's no longer 1-octanol. It is 1, 2, 3, 4, 5 from this side, and 1, 2, 3, 4 from this side. So we always take the number that's smaller, or the number that's closer to an end. So we're going to call this 4-octanol. Who's that?
Caitlin.
This 4-octanol would be considered a secondary alcohol because the carbon holding or bonded to the hydroxyl has 2 carbons bonded to it. So secondary has to do with the number 2, so it would be a secondary alcohol. Now I've changed the position of the hydroxyl group again. I put the OH here, and I added a methyl group, which is 1 carbon with 3 hydrogens bonded to it, to the other side of this carbon. So now, in order to name this, we know that it's octanol, but this time the hydroxyl group is at the second carbon. We count closest to any end, so 1, 2. And it also has a branch, which is a methyl branch because it has only 1 carbon on the branch. And so the name of this alcohol is 2-methyl, for the fact that the methyl group is at the second carbon. 2-octanol, showing that the hydroxyl group is also at the second carbon. And this type of alcohol is a tertiary alcohol. Tertiary has to do with the number 3, and you'll see that the carbon that's holding or bonded to the hydroxyl group has 3 other carbons bonded to it, and hence we call it a tertiary alcohol. This is week 26, page 2, number 12. Draw a structural formula for 1,2-ethane-diol. What type of alcohol is it? So in order to draw this structure, we have to look at it. We have 2 numbers at the beginning, which shows us that there are going to be 2 things attached to this molecule. We see that OL is at the end, showing that's an alcohol. We see this prefix di, meaning 2 here, So if there's two alcohols, that means there has to be two hydroxide ions attached to the parent chain. And the parent chain we see is ethane or ethane, which is a parent chain that has two carbons. Remember methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, decane for all of the alkanes. So let's start by drawing two carbons for the parent chain. So we have two carbons showing that it's an ethane. We show that each carbon has 4 possibilities for bonding. Now since it's a diol, we know that the two particular hydroxides have to be attached to this. One has to be attached to each carbon because it's telling us here that one is at the first carbon and one is at the second carbon. And then the rest of the bonds are going to be bonded with hydrogens. So the next thing the textbook asks is what type of alcohol is it? And anything that says diol at the end is a diol. That means it has two hydroxides attached to it. This is week 26, page 2, number 14. What is the IUPAC name and the common name for this condensed structural formula? The first thing I'm going to do here is circle all of the carbons. Now I'm going to try to identify what is bonded to each carbon. And if I see here, carbon has 3 hydrogens around it, and then it can be bonded to one other thing, which would be the oxygen. It cannot be bonded to this carbon because it would then have 5 bonds, and that wouldn't work. Therefore, we see that this oxygen is coming in between the 2 carbons. Now we know that this oxygen is not a hydroxyl group because a hydroxyl group would have to have an OH together, and this is just a plain O by itself. And therefore we see that there is a hydrocarbon chain on this side of the oxygen and a hydrocarbon chain on this side of the oxygen, which makes it an ether. Now in order to name this ether, we have to figure out which of the 2 hydrocarbon chains is the parent chain, and the parent chain is going to be the longer one. So the one on the right of this particular molecule. 1, 2, 3, 4, 5. This parent chain has 5 carbons, and so it will be called pentane. Now we have to identify the name of the other smaller hydrocarbon chain, and since there's only 1 carbon, we're going to call it methane. But since it's an ether, which is 2 hydrocarbon chains bonded to an oxygen, instead of the ane ending, we're going to give it an oxy ending, showing that there's an oxygen there. So this will be methoxy. So we have meth, we have oxy for the O in the middle, and we have pentane for the hydrocarbon chain on the right, methoxypentane. Now we can also name this by its common name, which names the 2 hydrocarbon chains as if they were branches, giving them the YL ending. So we see that this molecule has a methyl group and a pentyl group, and it's an ether because there's an oxygen in the middle, so we can call it methylpentyl ether. Week 26, page 2, Number 16. Give the IUPAC name and the common name for the ether with the following condensed structural formula. So we see that this particular ether has a methane group on both sides of the oxygen. There's one carbon over here, and there's one carbon over here, which means that there's a methyl group on both sides, and neither one is longer than the other, but we're going to name it as though one is longer than the other. So we'll name the first meth, oxy for the O, methoxy, and then methane. Now, since both of these groups, if they were branches with the YL ending, are the same, we have to give them a prefix of di to show that there's two. And the common name would be dimethyl, meaning there's two methyls and it's an ether. Dimethyl ether. Week 26, homework sheet, page 3, number 6. Name the molecules shown. So if we look at this condensed structural formula, we can see that there's an oxygen that's double bonded to the carbon in the middle of the molecule, and we call that a carbonyl group. Now, when there's a carbonyl group, it could be at the end of a hydrocarbon chain, and that would be an aldehyde, or it could be in the middle of a hydrocarbon chain, and it could be a ketone. This particular one is in the middle of the hydrocarbon chain, indicating that it's a ketone. The formula they give for this basically shows that there are two different hydrocarbon groups, R prime and R. They could be the same, and they could be different. They're both bonded to the carbon, which is bonded doubly to the oxygen in the carbonyl group. Now, since this long chain is not interrupted by anything, and all of the carbons are in the chain together, we're going to count all of the carbons, even though the carbonyl group is kind of separating it. So we have 1, 2, 3, 4, 5, 6 carbons, and that would give us a parent chain called hexane. And since the carbonyl group is attached to this hexane, we can't call it just plain old hexane. We have to give it an ending to show that it is a ketone. And we use the same ending as the word ketone, O-N-E. Now, the last thing we have to do when naming this molecule is we have to tell where the carbonyl group is. And it's going to be on the number, if the lowest number when we count from either side. So 1, 2, 3 carbons from this side, and 1, 2, 3, 4 from this side. So we'll call it 3-hexanone. Week 26, page 3, number 8, write the structural formula for octanol. Now with the Al ending, we know that's an aldehyde, and we can write the general formula for an aldehyde. We know that an aldehyde has a parent chain of a hydrocarbon, which is the R. There's a carbon at the end of it that's attached to an O with a double bond, which is the carbonyl group, and a single hydrogen. Now, if it has the octane root word, then we know that there are 8 carbons. We know that at one end is the carbonyl group. The rest of the molecule is going to be just a molecule of octane with all single bonds bonded to hydrogens. A couple things to notice. One, that this carbon doesn't have a hydrogen coming down from it because it already has 4 bonds. 1, 2, 3, 4. Another thing to notice is that the carbon that's attached to the carbonyl group is counted as part of the 8 carbons in the parent hydrocarbon chain. Now, if you were going to write a condensed structural formula for this, you start with the carbon at the end here, CH3, and then every one of these in the middle are the same. 1, 2, 3, 4, 5. So we can show that there are 5 CH2s by putting the CH2 in parentheses and giving it a subscript of 5. Then at the end here, I'm sorry, there's 6. At the end here, we have another carbon that has a hydrogen and an oxygen. Now notice the order that I put the hydrogen and the oxygen in. If I put COH, then it would be a hydroxyl group that is part of an alcohol, and that's not what we have here. We have a carbonyl group, and so we need to make sure we put it HO in that correct order. Week 26, page 4, number 4, write the condensed structure for 5-methyl hexanoic acid. Now, an acid with the oic ending and then the word acid, we know is a carboxylic acid, and we know that that has a functional group of COOH. We also see that there is a methyl branch that's attached to this particular molecule, and we see that there are 6 carbons because it's called hexanoic acid. So hexane indicates 6 carbons. So let's replace the R here with a chain of hexane. Notice that I counted the carbon. That's part of the carboxylic acid group, or the carboxyl group, as part of the 6 carbons in the chain of hexane. 1, 2, 3, 4, 5, 6. And now when we count to decide where to put this methyl group, which is at the 5th carbon, we have to count from this side here where the functional group is. So this would be 1, 2, 3, 4, 5. And it's a methyl group, so we're only putting 1 extra carbon in this branch. Now the rest of these carbon bonds are going to be filled with hydrogens. Now the problem told us to write the condensed structural formula for 5-methyl hexanoic acid. So we're going to start with the ending carbon, and that gives us a CH3. Now our next carbon has a C for carbon. It's bonded to 1H, and it's also bonded to a branch of methane. We're going to put that branch of methane in parentheses. And now we have 1, 2, 3 CH2s. And then we have our carboxyl group. The carboxyl group is always written COOH. It helps you to identify it as a carboxylic acid. Notice that this, you might think, was a CH3 in the middle of the chain, but CH3 cannot be in the middle of the chain. Therefore, that will hopefully help you to realize this has to be a branch off of this carbon that it comes after. So this carbon is bonded to 3 hydrogens and 1 other carbon. This carbon is bonded to the carbon over here. 1 hydrogen makes 2. This carbon as the methyl branch makes 3, and then the next carbon makes 4 bonds. As you can see right here, 1, 2, 3, 4. And that is the condensed structural formula for 5-methylhexanoic acid. Week 26, page 4, number 5. Name the carboxylic acid with the following condensed structural formula. So we look at this formula and we see that there is a carboxyl group at the end here. So this will have to be carbon number 1. We have 2 more carbons in the chain here. CH2, it's got 2 hydrogens bonded to either side of it, and then on the chain sides it's bonded to this carbon and this carbon over here. So there's 2 of those. Here we have CH3 and here we have CH with CH3 in parentheses. Now we know we can't have CH3 in the middle of a chain. CH3 can only be at the end carbon of a chain, so this must be a branch that comes out of this carbon. So since it's a branch that has only 1 carbon, it's going to have to be a methyl branch. Here is another carbon and another carbon. So the chain, the parent chain itself, has 1, 2, 3. We won't count this because this is a branch. 4, 5, 6. So it's going to be hexane. And since there's a carboxyl group at the end here, we know it has to be a carboxylic acid. So we're going to put the ending oic and acid. Hexanoic acid. Now there's one more thing we haven't identified as part of this molecule is the methyl chain here, or methyl branch, I mean. Now, what number do we give this methyl branch? We could say 1, 2, 3 is closer than 1, 2, 3, 4, but if the carboxyl group is over here, then this would be the first carbon. 1, 2, 3, 4 methylhexanoic acid. Week 26, page 4, number 7. Name the ester formed from acetic acid and ethyl alcohol. So the first thing we're going to do is we're going to draw out the structures of each of these. So here we have acetic acid. You can see the carboxyl group, and you can see that there's another carbon in the chain. It's got 2 carbons. Then we're going to draw out ethyl alcohol. Ethyl alcohol has 2 carbons. We know that because of the ethane root of the word. We're going to show that it's an alcohol by adding the hydroxyl group at the end. The rest of the bonds are filled with hydrogens. So when a carboxylic acid and an alcohol are added together, an ester is formed and water is also formed. So here we have the hydrogen plus oxygen, and hydrogen yields water. So when these are added together, the water is released, and we see that that oxygen here now bonds with the carbon, and we have that carboxylic group, but there's no longer a hydrogen with this oxygen. Instead, there is a hydrocarbon chain. So when we show an ester, we show the carboxylic group with an R instead of an H. And in this particular ester, we have ethane on one side and we have ethane on the other side, because both sides have 2 carbons. So we're going to call it ethyl ethanoate. 08 is the ending that we use for an ester. Usually we treat the smaller chain as a branch and give it the YL ending, and the larger chain as the parent chain and give it the OATE ending when we have an ester. Week 26, page 4, number 9, write the condensed structure for methyl 2-methylhexanoate. Methyl 2-methylhexanoate. Methyl here is showing us that there's a branch named methyl which has 1 carbon. It's at the 2nd carbon of the parent chain. This methylhexanoate tells us that the ester has 1 branch with only 1 carbon and 1 branch with 6 carbons. So let's draw that out to start with. Here's the methyl group with 1 carbon, CH3. And then the hexane group has 6 carbons. Now this hexane group has to have a carboxyl group at the end where it attaches to the methyl group. Therefore, we know that this must be 2 hydrogens because it's connecting with that oxygen. Now we have to figure out where to put the methyl chain. So the methyl branch, we're going to count from the functional group right here, 1, 2, and we're going to put the methyl branch right here. For the condensed structural formula, I started on this end. This is CH3 because 3 hydrogens will be bonded around here. We have 1, 2, 3, 4 CH2s. So we write CH2 in parentheses with a 4 as a subscript. Then we have COO, just like a carboxyl group, but instead of the H, we have a CH2. And that's what makes it an ester. This is week 26, page 5, number 5. Name the compound shown here. Now if we look at this compound, we see that the only thing in it that is not carbon or hydrogen is nitrogen. And there are 2 possibilities. It could be an amine or it could be an amide. An amine has an ammonia group, NH2. An amide has an ammonia group, but it also has the oxygen of a carbonyl group. So we don't see any oxygen in this one, so it must be an amine. And we know that the suffix added to the root of the carbon chain for an amine is amine. Now if we look at the structure of this molecule, we see that there's a chain of carbon, and the 3rd carbon here is bonded to the carbon before it and the carbon after it, that's 2, the hydrogen, and it's also bonded to this ammonia group. So if we count the carbons, we see 1, 2, 3, 4, 5, 6, 7. So I've made a 7 carbon chain here. This nitrogen is not in the middle of the carbons. The nitrogen is attached at the side, and we know that because 1, it's in parentheses, and 2, if the nitrogen was in the middle of this particular chain, let's just show it. Let's pretend the nitrogen was here. Nitrogen can only bond to 3 other atoms because nitrogen has a valence electron shell of 5 valence electrons, so it only needs 3 more in order to have a complete valence electron shell, and therefore it can only bond to 3 things. So the nitrogen could only have 3 bonds. It would have have to bond to the 2 carbons next to it. And where are those 2 hydrogens going to go? There's nowhere for them to go. It could only have 1 hydrogen. So this nitrogen is not in the middle of the chain. We see from the condensed structure that the nitrogen is attached to the 3rd carbon from the left. 1, 2, 3. So here's the nitrogen with its 2 hydrogens, the ammonia group. The rest of the carbons are surrounded by hydrogen atoms, and I'm not going to draw them all out this time, but every bond has a hydrogen atom. So the way to name this is to use the prefix or the root for 7, since there are 7 carbons, and that's hept. So we have heptane, which is a 7-carbon chain. Get rid of the E and add the ending. So we have heptanamine. Now we have to tell which carbon the ammonia functional group is bonded to. If we count from the right, 1, 2, 3, 4, 5, it would be the 5th carbon. If we count from the left, 1, 2, 3, it would be the 3rd carbon, and we'll take the one that's least. So it would be a 3. Week 26, page 5, number 7. Write the condensed structure for 2-propanamine. So we see the amine ending, which tells us that there's going to be an amino group, which is NH2. And we have the root prop, which means 3. So there'll be 3 carbons in the chain. And the number 2 tells us that the amino group is attached to the 2nd carbon. So let's go ahead and draw that. There's our 3 carbons for prop. Now we're going to put the amino group in, and we put it at the 2nd carbon. It doesn't matter which side we count from, since from either side the middle one is number 2. And all the other bonds will have H's on them, hydrogens. Now in order to write the condensed structure, we're going to start with the 1st carbon, and there are 3 H's bonded to it, 3 hydrogens, so we have CH3. The 2nd carbon has a C, it also has an H, a hydrogen, and it has an amino group, which will be put in parentheses. The 3rd carbon has only 3 hydrogens bonded to it. And this is the condensed structure for 2-propanamine. Week 26, page 5, number 10. Name the compound. When we look at this compound, we see an amino group. We also see an oxygen. That tells us that it's not an amine, but an amide. We can see that there are 3 carbons and 1 oxygen, which is the carbonyl group, and an amino group. So let's draw that out. So here's our chain of 3 carbons, and the root for 3 is prop, so we know that prop is going to be in the name. Now at the end of this molecule we see that there's an oxygen carbonyl group, which is an oxygen bonded with 2 bonds. So if we put 2 bonds up there, we need to get rid of one of these other bonds because carbon can't have 5, so we'll get rid of this one. We also see that that carbon is bonded to an amino group. The rest of the carbons are filled with hydrogen bonds. I mean, not hydrogen bonds. are bonded to hydrogen. So since this is an amide, we give it the ending amide. And the name for this compound is propanamide.